In this section, we'll be talking about tangent vectors as well as normal vectors. In Calculus 1, you learn about finding the slope of a line that's tangent to a curve. All right, well, how do you do that? Oh, well, that's given by the derivative of the function at that point. Once you know the slope, then you can easily find the equation of its line. Okay? In this section, we're going to find something related. Let's begin with a vector-valued function. So let r of t, and we're going to need some derivatives, and we're going to need those derivatives to exist and be continuous. So we're going to need a smooth curve. Let r of t represent a smooth curve on an open interval I. Remember, when we say a smooth curve, that means that the derivatives of the components exist and are continuous. At least they do on some particular interval I. Then the unit tangent vector the unit tangent vector is defined as, so first of all, the symbol for that, we're going to have a capital letter T for tangent. We'll put a little arrow over it because after all it is a vector, the unit tangent vector. And it is coming from a position function that's parameterized with the variable t. So it'll be also parameterized with the variable t. So this would be the tangent vector, the unit tangent vector, and it's given by, well, probably the most obvious way to do it is to say, oh, well, it's the derivative of the vector-valued function. So here it's going to be given by r prime at t. Now you might say, why are you putting it so high? Well, it's a unit tangent vector, meaning it's got length 1. Well, that means we're going to take this and we're going to divide it down. So if this has a magnitude of 20, well, then you could divide it by 20, and that would get it down to a magnitude of 1. Whatever the magnitude of this is, if you just divide by that number, the magnitude will be a unit magnitude. So here, we're going to define it as the derivative of r divided by the magnitude of the derivative of r. This is our unit tangent vector. And here this is so long as r prime of t is not equal to 0. So here we're making the stipulation that as long as this is defined, it's called the unit tangent vector. One thing that I've already stated, and I'll make it as another note, note that the magnitude of the unit tangent vector is equal to 1. Because when you take a vector and divide it by its own magnitude, you get a vector of magnitude 1. You get a unit vector. So since this is a unit vector, its magnitude is 1. Okay. So for example, let's go and find the unit tangent vector. Incidentally, notice here we don't make any mention of whether we're on the plane or in space. It doesn't matter. This is always true as long as you can define the derivative. So for example, let's go ahead and find the unit tangent vector of r of t equals e to the t cosine of t, comma, e to the t. And we're going to do this at a specific point, at a specific time index, t equal to 0. So find the unit tangent vector of this at time 0. All right, so we begin by finding the derivative of the vector-valued function that gives us the position. Let's find r prime of t. All right, well, that's done component-wise. Here you're going to need to use the product rule. Okay, so the derivative of the first part, e to the t, times the second part is the cosine of t, plus the derivative of the second part, the derivative of the cosine of t is negative the sine of t, times e to the t. So that's going to be minus e to the t sine of t. And then here the derivative of e to the t is just itself. All right, so there is our first derivative. Now we need to find the magnitude of that derivative. Okay. Now, as long as all you're doing is you're looking for the unit tangent vector at a particular point, you can just go ahead and plug in 0 now. And then once you have that plugged in, you'll get just a vector with constant components. Then finding the magnitude of that will be reasonably simple. If you were not looking for it at a particular time index and you were just looking for the unit tangent vector in general, you'd have to find the magnitude of this whole thing. Right? So just be mindful of that fact that will take a bit longer. Right now, I'm going to go ahead and do it the longer way. And I'm going to say, okay, let's go ahead and find the magnitude of r prime of t. And then I'll do it the shorter way. Right? Here, sometimes it will be necessary to do it the longer way because we're not going to have a particular time index. We're just going to say find the unit tangent vector in general. And then the short way will be a lot easier if you do have a time index. All right? So the longer way would be to just take this without plugging anything in and then find its magnitude. We're going to take the square root of the sum of the squares of these things. Like this. All right, well here we're squaring a binomial, so let's actually multiply that out. When you square a binomial, that's the first thing squared. So that'll be e to the 2t cosine of t squared, and then plus the second thing squared, plus e to the 2t sine squared of t. And then here you would multiply these together and double. All right, if you have a plus b squared, going back to basic algebra, you would expand this as a squared plus b squared plus 2ab. Since that one has a minus in front, 2ab would end up being a negative. So we'd end up with minus 2 this times that. Okay, well e to the t times e to the t is e to the 2t cosine of t times sine of t. Plus, and then squaring this one, we just multiply the powers together, e to the power 2t. Notice right here we have a Pythagorean identity. If you factor out e to the 2t, right here, if you take e to the 2t, factor that out, you're left with cosine squared of t plus sine squared of t, which is the Pythagorean identity. That's equal to 1. So that's, if you take this plus this, you're left with e to the 2t that you factored out times 1. In other words, you're just left with e to the 2t. Here you have another, let me just write it this way, minus 2e to the 2t cosine t sine t. And then you have plus another 2e to the 2t, which, you have another e to the 2t, which when you add those together, this one plus that one over here, in fact, let me just write it, that would combine as 2e to the 2t. So here we could write that as the square root of, this is 2e to the 2t minus 2e to the 2t times the cosine of t times the sine of t. And that would be our magnitude. So now you can take this and divide by each of those. Oh, sorry, I said that backwards. Take each of these and divide by this. So you would take all of that over this, comma, that over this. Because after all, that's what it means to divide by a scalar. You're simply dividing each component by that scalar. Okay. So here, that would be finding the derivative. And then, that would be finding the derivative, and that would be finding the magnitude. And then once you did that, once you took this over that one, and then this over that one, then you could plug in 0. Okay? Of course, it would be a little simpler here. Since we know that we're plugging in 0 in the first place, we may as well just go ahead and plug it in from the beginning. All right? So here, the unit tangent vector is equal to, and here I'm just going to write this out as e to the t cosine of t minus e to the t sine of t over the square root of 2e to the 2t minus 2e to the 2t cosine of t sine of t, comma, and then same thing over here. We could take, oh, you know what? We could actually simplify this a little further. Here, notice that 2e to the 2t is a common factor. We can pull that out. And so we have 2e to the 2t times 1 minus the cosine of t sine of t. But then notice I know how to take the square root of e to the 2t. So that would just be e to the t times the square root of 2 times 1 minus the cosine of t sine of t. So here, if I was going to divide by that one, I could just take the e to the t on the outside times the square root of 2 times 1 minus cosine of t times the sine of t, which is nice because now this e to the t divides those e to the t's. And then over here I'd have e to the t divided by this thing again. They're going to have the same denominator, e to the t square root of 2 times 1 minus cosine of t sine of t, which the e to the t's divide out, and you're simply left with cosine of t minus sine of t over the square root of, here, I may as well just multiply that in here, 2 minus 2 cosine of t sine of t, comma, here these divide out, and you're left with 1 over the square root of 2 minus 2 cosine of t sine of t. So this would be our unit tangent vector regardless of t. So if in the beginning you didn't have this, and you were just told, hey, find the unit tangent vector, this would be your answer. Like that. And then, now I have to plug in 0. Okay, you could plug in 0 to all these and get some result. If, however, you start with this, it may be easier to go the other way. So here, if you have t equals to a number to start, it's simpler to do the following. First, find r prime of t. So just like we did up here, that very first step. But now, go ahead and find r prime of your number. In this case, r prime of 0. Okay, so in this case, I would just plug in 0 to all these numbers. Okay, so let's see what that is. R prime at 0 would be, that's e to the 0, which is 1, times the cosine of 1, which is also 1. Oh, that should be a vector. There we go. And then e to the 0, that's also 1. Okay, so that is our derivative, r prime at time t. So now we can find the magnitude of r prime at that time index. We're going to find the magnitude of r prime at 0. And that's going to be the square root of 1 squared plus 1 squared. Well, in other words, it's the square root of 2. All right, we're finding the magnitude of that. That's the square root of 1 squared plus 1 squared. That's the square root of 2. And so we can put this together, and the unit tangent vector at 0 is equal to, we're going to take this vector 1, 1, and we're going to divide by the magnitude of that vector 1 comma 1, which is root 2. Or in other words, we're going to get 1 over root 2 comma 1 over root 2. Or in other words, we get the square root of 2 over 2 comma the root of 2 over 2. Just like that. So once again, if you do not have the time index to start, you have to go through all this. You have to take the derivative, find the magnitude of the derivative and simplify, and then divide and simplify. However, if you do have this, although you could do this and then plug in 0 at the very end, you're probably better off plugging it in, taking the derivative first, the same way we did, but then after that, plug in 0 to find r prime at 0, or whatever number you need, find the magnitude of that vector, and since those are all constants, things will be much simpler to divide out and simplify. So either way, we get the same result, root 2 over 2, comma root 2 over 2. Now, we'll see another example of this in a moment, but before we do, recall from a previous section, when we talk about the properties of the derivatives of vector-valued functions, one of the results that we get, which at the time I said was, it may seem pointless, it may seem like it's not particularly grand or useful, but we'll get use out of it later. Well, we're at that point now. Recall, if you take the dot product of a vector-valued function with itself, and you get a constant, then if you take the dot product of that vector-valued function and its derivative, you must get 0. All right. Note, by definition, if you multiply a unit tangent vector times itself, that's got to equal to the magnitude squared. Right? That's one of the properties of the dot product. If you take the dot product of a vector with itself, that's the square of its magnitude. But by definition, since this is a unit tangent vector, that's got to be the square of 1. Or in other words, it's 1. Oh, so here we have a situation where the dot product of a vector with itself is a constant. Oh, okay. So that means that t dotted with t prime is equal to 0. Oh, but whenever you have a dot product of two vectors and you get 0, we call those orthogonal. Thus, t and t prime are orthogonal. This brings us to a definition. Let's begin with a vector-valued function r of t. Let r of t represent a smooth curve on an open interval. Which we'll call I. Let t, the vector-valued function t of t, let's let that represent the unit tangent vector as defined in the previous definition. Finally, let t prime at t not be identically the 0 vector. It can have 0 components, but it should not be the 0 vector. Then, what we're going to call n of t given by the derivative of t over the magnitude of the derivative of t is called the principal unit normal vector. At t. As a quick visual of what it is that we've defined in relation to what we've previously defined, here's a curve. It's got a particular orientation. If you take the derivative at a particular point, you're going to get a tangent vector. Let me put that in pencil. We're going to have a tangent vector. Oh, but that's just some length. We don't even know what length it is. Oh, but if we divide it by just the right length, we'll scale it down so that it is exactly 1 unit long. Oh, that's called the unit tangent vector at the point t. Okay? But now we find that if you take the dot product with t and its derivative, you get 0. Or in other words, a vector that's orthogonal to the vector t, that's perpendicular, is going to be its own derivative. Okay, so orthogonal to this would be this one here, or this one up here. Whenever we talk about the principal unit normal, note there are two different normal vectors, ones that are perpendicular to this one. Whenever we talk about the principal one, we're talking about the one that is toward the bend, toward the curve. So this is concave this way. It's the one facing into the concave portion. Facing out would be the other unit normal vector, but the principal one is the one facing in toward the curve. Okay. Here, if you take the derivative of t, that will give you t prime of t. That would be orthogonal to this one. But now if you take that one and you scale it back so that it's 1 unit in length, oh, well then that would be your principal unit normal vector. Derivative gives you something tangent, scale it down to give you the unit tangent. Derivative gives you something perpendicular, orthogonal to that, scale that back to give you the unit normal tangent, the unit normal vector, just like that. So as an example of this, let's go ahead and find the principal unit normal vector to r of t equals the square root of 2t. The t is on the outside of the square root. That's just a coefficient. Square root of 2t, comma, e to the t, comma, e to the minus t at time index 0. Okay. First, we're going to need to find the unit tangent vector. Right? And then we're going to take the derivative of the unit tangent vector to find the unit normal vector. So here we'll have an example of the previous problem. Now, in the previous problem, we saw that you can plug in your number. As long as you know that t is equal to 0, t is equal to 1, t is equal to 2, you can go ahead and plug in that number and you get your result much more quickly. Right? Unfortunately, you won't be able to do that first. You say, what do you mean first? Well, in order to compute the unit normal vector, first you need to compute the unit tangent vector. And then from the unit tangent vector, then you compute the unit normal vector. Okay? But if I compute the unit tangent vector by plugging in a number, remember, I get just a vector with constant components. If I take the derivative of that, though, if I call this my unit tangent vector, and I take the derivative of this, I'm going to get 0, 0. And that's always going to happen. Okay, well, I know for a fact that my unit tangent vector won't always be 0, 0. There's no way that could be the case. Okay, that means we can't just plug in the number. What that means is we're going to have to find the unit tangent vector the long way, meaning this stuff up here, algebraically, without any constants. And then, once we take the derivative of that one, then we can plug in the number. Basically, you can plug in the number once you're at the last stage. Here, the last stage was, well, there's only one stage. You're going from position to tangent. Okay, so at that stage, you plug it in. But if you're going to go all the way to the normal vector, you go from position to tangent using just variables, no constants, and then you go from tangent to normal, and that's when you can plug in your constants. All right, so let's go and take a look at how that works. First, we need to find r prime of t. Okay, can't plug in the number, got to use that as it is. All right, well, that's not too bad. The derivative of root 2t is just root 2. The derivative of e to the t is going to stay e to the t. And the derivative of e to the minus t is e to the minus t. But then because of the chain rule, the derivative of minus t is minus 1. I can write that as minus 1 e to the minus t, or more simply just minus e to the minus t. All right, now I need to find the magnitude of r prime of t. Okay, well, that's going to be the square root of the sums of the squares of those three components. Root 2, e to the t, and minus e to the minus t. All right, well, that's going to be the square root of, if I square the square root of 2, that just gives me 2. If I square e to the t, I get e to the 2t. And if I square minus, well, squaring a minus gives you a plus, square e to the minus t squared, it's hard to see that minus, there you go, e to the minus t squared, now those are just multiplied together, and I will get plus e to the minus 2t, like that. Notice here that this can actually be simplified. I can actually factor this. This is going to be the square root of, I can factor this as e to the t plus e to the minus t quantity squared. Notice if I take e to the t minus e, or plus e to the minus t times itself, in other words, e to the t plus e to the minus t squared, that would be e to the 2t. That would be e to the 0, because when you add those powers, t minus t would be 0. That would also be e to the 0, and that would be e to the minus 2t. But e to the 0 is equal to 1, so 1 plus 1 would make that 2. So that would be 2 e to the 2 plus e to the 2t plus e to the minus 2t, which is that, 2 plus e to the 2t plus e to the minus 2t. Which means that this factors into e to the t plus e to the minus t times itself. Oh, but now the square and the square root, I don't have to worry about branches of anything. I don't have to worry about pluses or minuses because this is always positive. E to the t is always positive. And so is e to the minus t. So here this is just going to give me e to the t plus e to the minus t. Will things always simplify that nicely? No, of course not. But we're in math book land where all the problems we give you will either simplify out nicely or they won't need to simplify out nicely, like in the last example. Okay, so here, this simplified out fairly nicely. So now, third, let's go ahead and find the unit tangent vector. And of course we do that by just taking r prime of t and dividing it by the magnitude of r prime of t. Okay, so take those components and divide by e to the t plus e to the minus t. So that's going to be what? Root 2 over e to the t plus e to the minus t, comma, e to the t over e to the t plus e to the minus t, comma, e to the minus t over e to the t plus e to the minus t. So there's my unit tangent vector. Okay? Now, I can't plug in the number yet because the next stage, I'm going to have to take that unit tangent vector and take its derivative. If I plug in the number right now, it's going to give me constant, 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 which means my derivative will be 0, 0, 0. And, well, I'm pretty sure that the unit normal vector is not always 0 100% of the time. Right? If it were, we would just say, hey, do you see the symbol? That's equal to the 0 vector. And then we would just move on. All right, so now we need to take the fourth. We need to find t prime of t. Okay, well, things are not terribly bad here. Here we're going to take the derivative of this expression here, one component at a time. Now that does look a little unpleasant. I have to use the quotient rule. And I have to use the quotient rule 3 times. And I have to use the quotient rule the 3 times with the same denominator each time. I could do that. That just sounds like a pain. You know what I can do though? I'm going to take advantage of one of the properties of the derivative. And that's the fact that the product rule still exists. Here, I'm going to go ahead and write this in a different form. Here, I have a common factor of e to the t plus e to the minus t. So let me factor that out. I'm going to write that as 1 over e to the t plus e to the minus t. And once I factor that out, what's left inside is root 2 comma e to the t comma e to the minus t. These two mean the same thing. If I distributed that out, that would give me that. Okay. But now, this is now the product of a real valued function and a vector valued function. And we saw in the same section that we saw this statement right here, this statement up here, where we saw the properties of the derivative of vector valued functions. Recall that if you take the derivative with respect to t of a real valued function times a vector valued function, then we're going to use the product rule, where it's going to be the derivative with respect to t of the first one times the second one, plus the derivative of the second one times the first one. So it's the product rule. So here, at least then, I still have to use the quotient rule here, but at least I don't have to do it 3 times. All right, so let's give this a try here. Let me take the derivative of this first part. Let me do that over here. Let's see, that I can write that as e to the t plus e to the minus t to the minus first. And that's because it's in the denominator. And now I can take the derivative of that. I'll use the chain rule. Take my minus 1, bring it down. And then subtract 1 from the power to make that a minus 2. But then, because of the chain rule, I have to take the derivative of the inside and multiply it in. So that's going to be the derivative of e to the t, which is e to the t, and the derivative of e to the minus t, which is minus e to the minus t. Okay. All right, so then that's going to give me the derivative of this one. Since that's got a negative 2 power, I can bring that to the denominator. So that'll be e to the t plus e to the minus t squared. Okay. And then in my numerator, I have negative 1 times all of this stuff. Okay, well then let me take this, turn it into a positive, and let me take that one as a negative. So that'll be e to the minus t minus e to the t. I'm just distributing that negative 1 to this part right here, and this part, I'm bringing it down to the bottom. So that's the derivative of the first part times the second part. Plus, now I need to take the derivative of the second part. That one's relatively nice. The derivative of square root of 2 is 0. The derivative of e to the t, that's e to the t. And the derivative of e to the minus t, that's minus e to the minus t, times the first part. Like that. Okay. So now that's the derivative of my unit tangent vector. Now you can plug in the point. All right, because now we're going to use this and its magnitude to find the unit normal vector. So now we can go ahead and plug in the point, once you know what the derivative is. Fifth, let's go ahead and find t prime at 0. Now at this point you could continue simplifying this and then find the magnitude of this and then plug in 0. But at this point you're probably better served simply going with that value that you want. So here t prime at 0, that's going to be, well, we're just plugging in 0 to all of these. So e to the 0 is 1 minus e to the 0, that's also 1. Okay, so that's 0. And then that's 1 plus 1, that's 1. Okay, so that's 0 over 1. Oh, that whole thing is 0. Right? That's 0 over 1 times root 2. E to the e to the 0 is 1, and e to the 0 is, again, 1. But again, that's 0 times all of that stuff. That's just 0. If I plug in 0 over here, that's going to be e to the 0 is 1, plus e to the minus 0, well, that's also 1, and 1 plus 1 is 2. Okay, so this one will not be 0. That's going to be 1 over 2. That's already a constant 0. E to the 0, that's 1, and minus e to the 0, that's minus 1. So then that means that t prime at 0 is equal to, maybe a bit anticlimactically, it's equal to 0, comma 1/2, comma minus 1/2. And now we're almost done. This is the unit tangent vector at 0. Now we just need to find the magnitude of this and divide to get our unit normal vector. So let's find the magnitude of this unit tangent vector. That's going to be the square root of the sum of the squares of these components. All right, so 0 squared is 0. 1/2 squared is a quarter, plus another quarter. That's the square root of a half. Okay, so then that means that, well, here I can simplify that. That's 1 over root 2, like, which is the same as saying root 2 over 2. So now, finally, my unit normal vector at 0 is equal to, I'm going to take my unit tangent vector at 0, which is 0, comma, half, comma, negative a half, and we're going to divide the whole thing by this coefficient, which will be, I'll use this one since I'm going to reciprocate it anyway. I'm dividing everything by 1 over root 2. So here, 0 divided by anything is going to be 0. Here, 1/2 divided by 1 over root 2. Dividing by a fraction is the same as multiplying by a reciprocal, so that brings it to the top, making that root 2 over 2. And then same thing for this one, but with a negative in front. Negative root 2 over 2. And this is our principal unit normal vector at time 0. Note that you do eventually plug in 0, but you only do it once you've taken the last derivative you're going to need. So in the previous example, we only needed one derivative, and that was r prime. Once you found that, you were able to plug in the number, find the magnitude, and divide. But over here, we needed two derivatives. First, we needed to find r prime, but that's not enough. We need t prime. Okay, so we got to go through all this to find t, and then take t prime. Oh, but once that's the last derivative I'm going to need, because that's how I define my unit normal vector using that derivative, then I'm free to plug in my number. So don't plug in your number until you've taken the last derivative you're going to take. And that gets you your result. Okay, we're going to wrap up this section with an application of this unit tangent and unit normal vector. And it's a conclusion of something that started in the previous section when we start talking about acceleration and velocity. I mentioned something about acceleration and velocity being perpendicular, orthogonal to each other sometimes, but not necessarily. And I left it vague. Now, let's go ahead and, considering what we've seen here with the principal unit normal vector and with the unit tangent vector, let's consider the following statement. Theorem. And this is the theorem. We're going to be, it's about the acceleration vector. All right. Let's let r of t be a position vector. for the smooth curve, which we'll call C. Okay. Let T, I guess I can just continue the statement, T be the unit tangent vector and N be the unit normal vector, the principal unit normal vector. Then the acceleration vector A of t lies on the plane determined by T and N. Physically, what that means, you have a curve, and it doesn't, notice this doesn't mention anything about being on the plane or in space. This can be anywhere. So here, let's say we have a curve in space or whatever. Then let's say we find the unit tangent vector. Okay, well, let's say the curve is oriented this way. Then that means, let's just take it at this point because that's easy enough to draw. Let's say our unit tangent vector is going this way. Okay. Now let's say our unit normal vector, no, I guess we'll label that as t, like that. Let's say our unit normal vector is going this way. Now, of course, the unit normal vector is always perpendicular to the unit tangent vector. Okay. Now, the unit tangent vector is in the direction of the velocity. Right? The velocity at a single point on a curve is tangent to that curve. Now, of course, this is a unit tangent vector, whereas velocity doesn't have to be unit length, so that doesn't mean they're equal. But here, the velocity is in this direction. In other words, it's parallel to t. Okay? The acceleration need not be perpendicular to t. However, it does have to exist on the plane determined by n and t. Or in other words, here, the acceleration vector is somewhere on this plane. So now that does mean it could be in the direction of n, meaning they could be perpendicular, they could be orthogonal, but they don't have to be. But the acceleration does have to exist on the same plane as n and t. And that includes being in space. So even if you're in space, these two vectors are traveling in a particular direction, that acceleration vector must go along the plane determined by those two. Draw a rectangle with those vectors. That A has to sit on top of that rectangle. Now, the proof of this is fairly straightforward based off the definitions of the unit tangent vector and the principal unit normal vector. So let's take a look. Proof. We know that T is defined as R divided by the magnitude of R. Here, for the sake of simplicity, I'm going to leave off the arguments. I'm going to leave off R of T, T of T. All of these are, of course, with respect to the same variable. So for the sake of simplicity of writing out the argument, I'm going to leave off the arguments of these vector-valued functions. They are still functions of t, though. Okay, well, that's... oh, I'm forgetting my derivative. There we go. By definition, the unit tangent vector is equal to the derivative of the position function over the magnitude of the derivative of the position function. Okay, but another way of stating the derivative of the position function, that's just the velocity function, isn't it? So here that's the same as saying that's the velocity function over the magnitude of the velocity function. And here, that's a terribly messy way to write that. So let me try that again. That'll be the magnitude of r prime. There we go. Now this suggests that since this is a constant, I can always multiply this constant over here, and I get that the velocity is equal to a scalar multiple of t. So here, multiplying that over, I get that the velocity is magnitude of v times the unit tangent vector. Okay, so just like I mentioned over here, that doesn't mean that the velocity vector and the tangent vector are the same, but they are going in the same direction. One is parallel to the other, which this is another way of saying they're parallel. One's a scalar multiple of the other. Now, since, again, by definition, the acceleration vector is equal to the derivative of the velocity vector, and the velocity vector is equal to that, we could simply say the acceleration vector is equal to the derivative of this thing. Like that. But of course, when you take the derivative of a scalar times a vector, you're just using the linearity, meaning, oh, remember, that's just the regular number. You can always pull it out and take the derivative of just this part. So the linearity property of the derivative allows me to say, okay, well, that's just the scalar times the derivative of the vector. So that's magnitude of v times t prime. Oh, actually, I take that back. That statement is not true. Here, this is a scalar. It's a constant, but only at a particular value of t. Here, no, we're not stating any particular value. We're just saying, in general, the vector-valued function's magnitude. So in that case, it's not a scalar, which means you can't just say, oh, I'm going to go ahead and use linearity. Instead, what we're going to do is we're going to use the product rule. All right, so that's going to be the derivative of the first part times the second, plus the derivative of the second part times the first. Here, I guess I'll write it the other way around. So that'll be the magnitude times t prime plus the derivative of the magnitude times t. Right? Yeah, here this is not equal to a constant in general. Right? This is the square root of sum of squares of variable expression. This is a real valued function. It's only a scalar at a particular value of t. But here we haven't ever said, oh, we're looking at a particular value of t. In general, this may not be a vector valued function, but it is a function. So taking its derivative is not going to give me just 0. So I have to write that in there. So the derivative of the first part times the second plus the derivative of the second part times the first. Now here I'm going to write something just a little bit strange. I'm going to go ahead and take this expression and I'm going to randomly multiply it by the number 1. So you're going to multiply by the number 1? Yes, but I'm going to do it in a creative way because, well, what's math other than creativity, right? Creativity and lots and lots of rules. Here, I'm going to multiply by 1, but I'm going to use a very particular value of 1. I'm going to take the magnitude of the derivative of t over itself, which is the number 1. So technically, nothing's changed. Like this. But now I can reorder some stuff. Because after all, this is just a product, this times this times this, which means I can order things however I like. So I think I'll write it this way. I'm going to write this as the magnitude of v times the magnitude of t prime. So I'll put this one in front. Times t prime over the magnitude of t prime. Plus, and here I'll just write this as v prime t. So far nothing's changed here. Notice that by definition this is the principal unit normal vector. So here this is going to be the magnitude of v times the magnitude of t prime times the unit normal vector plus the derivative of the magnitude of v times t. But notice now that for any particular value of t, this is a scalar times the unit normal vector plus another scalar times the unit normal vector. For any value of t, we get a is equal to, this is just a scalar, times the unit normal, principal unit normal vector n, plus, I'll call this one scalar number 1, and this is scalar number 2, times the unit tangent vector t. Oh, but then that means that A is just the linear combination of n and t. So whatever A is can be made up of copies of n and copies of t added together. That must mean that they're all on the same plane. Since A is a linear combination, of n and t, that means they don't have any components that, there are no components of A that don't come from either n or t. That means they're all coming from the same plane. Then A I guess I'll say lies on the plane determined by n and t. This also gives us, hey look, not only is it, it's some linear combination, we know exactly what the coefficients of that combination are. So this gives us the last definition for our section. Here, let's start with this one. The derivative of the magnitude of t, here, the magnitude of v. If you take the derivative of the magnitude of the velocity, that's going to be denoted by a sub t. This is called the tangential component of acceleration. In other words, it's the part of acceleration that's going toward the unit tangent vector. This is the tangential, with an E, tangential component of acceleration. On the other hand, this other part, if we're going to take the magnitude of v times the magnitude of t, like this, that's going to be denoted by a sub n. This is referred to as the normal component of acceleration. As it lies in the direction of the, as it gives the coefficient of the normal vector, the component that's normal to that acceleration. And while these are the, left off a prime there, there we go. And while these are the definitions, there is a theorem that allows us a bit of leeway in computing these, a bit of more efficiency. Here, theorem, if we have a position vector, so let R of t be a position vector for smooth curve C. T of t be the unit tangent vector, and n of t be the principal unit normal vector. Then the tangential component of acceleration, which is given by the definition here, the magnitude of the velocity prime, can also be computed as v, the velocity vector, dotted with a, the acceleration vector, divided by the magnitude of v. And a sub n, the normal component of acceleration, which, as we see defined up here, as the magnitude of v times the magnitude of t prime, can also be computed as the magnitude of the cross products of velocity and acceleration over the magnitude of the velocity, like this. The proofs of this are left as an exercise. They're actually part of the homework. Proofs left to the student. So let's just take a look at a quick application of this. Note that oftentimes computing this just by definition can be reasonably simple and straightforward. However, computing this one by definition is sometimes a little more complicated because here the velocity is simply a straight up derivative of a position function. You can find its magnitude and derive fairly quickly. However, over here you'd actually have to find the unit tangent vector's derivative, which, as we saw in one of the earlier problems, can be rather involved. So here, this one, okay, it's not terribly difficult to go one way or the other. This one is a much easier way to go than by definition. So let's consider just one example here as we wrap up our section. All right, so example. Let's go and find the tangential and normal components of acceleration for the position vector given by r of t is equal to 3t, comma, minus t, comma, t squared. This first one can be computed either way. I think I'll just do it by definition just to show what that looks like. Here, by definition, the tangential component of acceleration, a sub t, is just you find the velocity, you take the magnitude, and then take the derivative. Okay. All right, so by definition, velocity is simply the derivative of the position function, which is 3 minus 1 and 2t. Okay, so now we want to find the magnitude of the velocity, the speed, and that's simply going to be the square root of the sum of the squares of those three components. That's a 3, a minus 1, and a 2t, which is going to be the square root of 9 plus 1 is 10, plus the square of 2t would be 4t squared, like that. So there we go. There's our speed. Notice we don't have any particular value of t. That's why earlier I made the mistake and I corrected and I said, oh, the derivative of this would be 0 because it's a constant. Wait, no. If we don't have any particular value of t, right, here we're not saying at any particular point, it's just, hey, here is our speed as a function, then this is a real valued function. Right? It's not a constant. It's real valued function. So now, if we take the derivative of that, well, then that's just a regular derivative, a Cal1 derivative. If you take the derivative of the square root of something, that's 1 over 2 root of that something. Oh, but then because of the chain rule, you would take the derivative of the inside and multiply it out. So the derivative of the inside would be, well, the derivative of 10 is 0, and the derivative of 4t squared would be 8t. Here these simplify down a bit, and you're left with 4t over the square root of 10 plus 4t squared. And there we go. That is our acceleration, the component of our acceleration. That is our tangential component of acceleration. There you go. I managed to say it right the third time. That's our tangential component of acceleration. All right? That's the component of acceleration that is in the direction of the unit tangent vector. Okay. Now, of course, if you had used this, that would also give you the exact same answer. Here, computing this by definition, this part right here is a little messy. So can you do it? Of course you can. Do you want to? Probably not. This would be far simpler. So let's go and take a look. First, we're going to need to find the velocity function. Okay, well, we already have that. We have that our velocity function is the vector valued function 3 minus 1, 2t. Next, we're going to need to find the acceleration function. Well, the acceleration function is, as we saw in the previous section, just the derivative of the velocity function. So in this case, that would be 0, 0, and 2. And after all, that's just v prime. Okay, so now, according to our theorem here, the normal component of acceleration, aside from the definition, can be computed by the cross product of v and a. Take the magnitude over the magnitude of v. All right, so let's go and find the cross product. We're going to need to find, let's see, v cross a. All right, well, we can find that let's see, v is 3 minus 1, 2t. 3 minus 1, 2t. A we found was 0, 0, 2. That should make things fairly nice with all those zeros. And here we go. That's going to be negative 2i. That's going to be 0j. And that's going to be 0k. Minus, that's going to be 0i. That's going to be 6j. And that's going to be 0k. So here, the cross product of v and a is going to be, well, let's see, minus 2i minus nothing else. Well, that's just minus 2i. My first component is minus 2. 0 minus 6. Okay, my second component is a negative 6. And then 0 minus 0, my third component is 0, like this. Now I need to find the magnitude of this cross product. So the magnitude of v cross a is equal to the square root of the sum of the squares of these components, minus 2, minus 6, and 0, which gives us the square root of, let's see, it's 36 plus 4 is 40 plus nothing. That's going to stay 40. In here, we can simplify that out. That's going to be 2 root 10. So now, again, our theorem states that it's going to be the normal component of acceleration is equal to the magnitude of the cross product of v and a, which we just found, divided by the magnitude of v. Okay, well, we know the magnitude of v. We computed that a lot earlier. That was this expression here. So now we're going to take the magnitude of v cross a divided by the magnitude of v, and that's going to equal to this constant, 2 root 10, divided by this function here, square root of 10 plus 4t squared, which we found in the previous part. Like that. And so that gives us our normal component of acceleration. This is the part of the acceleration that's going toward the normal vector. And those are our results. All right. So that brings us to the end of this topic and the end of this section. Should anybody have any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.